All right, let's go ahead and get started. Couple of things. Number one, just want to remind you, I'm going to be finishing up those last couple of Webwork problems from 7.6 center of mass, and I may even do a pumping problem for you guys. And then your homework, number 5, is due by Friday at the review session by 2 p.m. in Federal 113, where I will be going over it. And I also will be recording it for you guys for the few folks that can't make it to the review session or whatever. So you got something to study over the weekend, because guess when your test number 3 is going to be? On Monday, April 1st. That's right, April Fool's Day. So there it is. Also, to let you guys know, as I mentioned to you guys last time, when you check on your quizzes, because we had a little glitch in the system in terms of due dates and stuff like that, your quiz 7.6 on center of mass was due 15 minutes ago, just before class, over here on March 27th, as well as quiz 8.1, because I'll be going over 8.1 today. So hopefully you watched the awesome pre-section quizzes on those things and took notes off of it, because you should have realized something when you watched the awesome pre-section quiz on 8.1 with the video. It wasn't me, unless I transitioned or something or other. It was a young lady, that's right. I did all the Calc 1 videos. I did Calc 2 videos for Chapter 5, Chapter 6, and Chapter 7. So the math department came to me and said, John, you know, you're not the only person in the math department. You got some more people on this grant that will be working with you here. And one of them is named Beth Edders. And she is absolutely wonderful, very, very nice lady. And so she was called upon to finish up the Chapter 8 video, so I showed her how to use the system and stuff like that. So the rest of Chapter 8, it'll be a nice, soft female voice trying to tell you guys how to do sequences of series and stuff. All right, so just to let you guys know, a little change in the video system there. So let's go ahead and get started here. Now, just to recap this idea of center of mass, also known as centroid. Now, I try to give you guys basically the big pattern on this thing, and let's just go through it one more time. Now, the discrete case, when you have actually just a point mass system, is real simple. You get the mass, total mass, you add up all your masses. To get the moment about the y, you multiply the mass times the x coordinate and add them up. To get the moment about the x, you take the mass and multiply the y and add them up. And to get the center of mass, you take the moment about the y divided by the mass for the x coordinate. And for the y coordinate, you take the moment about the x divided by the mass. However, when you have a continuous case, now here's the big deal. It depends on whether the function is in terms of x or in terms of y. 90% of the time, and I use the word 90%, that means you got a 10% chance that it's not going to be, but 90% of the time we usually give you a function in terms of x. When the function is in terms of x, the moment about the y is going to be rho times integral from a to b of x times f of x top minus g of x bottom dx. And it comes directly from the shell method. The moment about the x is rho over 2 times integral from a to b of top function f of x squared minus bottom function g of x squared dx. And that would be the disk washer method, trying to catch a pattern on these things. Pi is equivalent to rho over 2, which means 2 pi is equivalent to rho being your density. And with this stuff, you have constant densities. Calculus 3, we'll talk about densities that change by functions, densities that change. And the last one is mass. Mass is equal to density times area, so that'd be rho times integral from a to b of f of x top minus g of x bottom dx. And again, same coordinate. X bar is the moment about the y divided by the mass, and y bar is the moment about the x divided by the mass. And just to reiterate, I put this set over here because of what they gave you guys one particular semester. I actually didn't do a problem with it. I just wanted to kind of walk you through these formulas, and they have changed. These formulas are what happens when the functions in terms of y. When your functions in terms of y, so your moment about the y to y, this ends up becoming the, quote, disk washer formula. And the moment about the x, but my functions in terms of y, that will be the shell method version of the formula, where you have right minus left instead of top minus bottom. Mass is still density times area, but the area would be right minus left. but your point is still going to be the same. The x-coordinates moment by the y divided by the mass, y-coordinates moment by the x divided by the mass. And so we did some problems last time on Webwork. This is probably the simplest problem we can give you. It's a great problem. If I give you force, a force function, and ask you to find the work, you integrate the force function based upon x. X represents distance. You integrate from a to b of force dx. It's a classic formula. So very simple form to get work. This is where I left off at, and I didn't get a chance to do this one. And of course, this is a Webwork problem for you guys. And it's all set up the same. And this one makes more work for you guys because they didn't give you any function. You're going to have to go find your own function. Here it is. A lamina has a shape of a triangle with vertices at the point -10, 0, 10, 0, and 0, 8. Its density, told you this is Webwork, density is rho is equal to 4. You're supposed to figure out what is the total mass, the moment about the x-axis, the moment about the y-axis, and where the center of mass is going to be located at. And this is more of a theory question than anything else. But the first thing you want to do is draw your picture. So I've got this triangular shaped region here. I got it at point -10, 0. So -10, 0 would be at this point right here. At the point 0, 10. So 0, 10 is up here on the y-axis. So excuse me, 0, 8. 0, 8 up here on the y-axis, 0, 8. And the point 10, 0 is over here, 10, 0. So here's the point 0, 8. Here's the point 10, 0. Here's the point -10, 0. And this is my triangular region. Okay? Now, we have a constant density throughout this region, and that density is 4. First question is, we're supposed to find the total mass. So for part A, the total mass. But what you should remember is the total mass is equal to rho, which is your density, times area. That's your formula. When we use the integral form, find the area is top minus bottom, dx from A to B, or right minus left dy from C to D, or whatever. But this one's a triangle. Do you actually need to come up with formulas for the bounds on this thing if you want to figure out the area of a triangle? No. Area of a triangle is equal to what? 1/2 the base times the height. The base is how long? If you're over here at -10 and you're going over here to +10, how long is your base? 20. So this has a base of 20. What kind of height do you have? The height is 8. So that'll be 1/2 20 times 8. 20 times 8 and half of that. Well, half of 20 is 10 times 8 is 80. Your area is 80. So your total mass would be 80 rho, but this is Webwork. And in Webwork, they actually give you a constant for rho. What's your rho equal to? 4. So 80 times 4 is how much? 320. And that's what you would put into Webwork. Does that make sense? Part B. What is the moment about the x-axis? To understand this, you're going to have to need the equations here. To figure out the moment about the x-axis is the tendency to rotate around the x-axis. Okay? So this is where I'm actually going to need my equations. But the trick to this problem, this is why I put this one on your notes instead of just let you guys have at it on Webwork, is use symmetry. We're talking about the idea of the moment of going around the x-axis. But the y-axis splits my region right down the middle. So if I really focus on this, to get the moment about the x-axis, what I need to do is if I focus just on one region right here, and I'll focus on this particular region right in here, okay, and that would be from the origin 0, 0 to the point 10, 0, and up here is still the point 0, 8, and I'm going to be, figure out what the moment about the x-axis of this region is going to be. And all I need to do is do what? To get the other little side of this thing, because it is the exact same region just on the other side of your y-axis. What am I going to do? I'm going to double it, right? So I do need the equation for this line. So I am going to have to come up with my own equations. It is a line, so I've got slope. Slope is equal to change in y with change in x, y2 minus y1 over x2 minus x1. That would be, this is the point 0, 8, up here at 8. Change in y, 8 minus 0, divided by change in x, 0 minus 10. That's equal to a negative 8/10, which reduces to a negative 4/5. So my slope is negative 4/5 on this problem. Okay? Now, I'm going to find the equation of this line. I'm going to use the point slope formula. Y minus y1 equals m times x minus x1. Y minus, I'm going to use this point up here. Y minus 8 is equal to my slope, negative 4/5 times x minus 0. I used the point 0.8 just plugged into this guy. And with my slope of negative 4/5. And that gives me y minus 8 equals negative 4/5 x. Or better yet, y is equal to negative 4/5 x plus 8. There is my equation of my line. Does that make sense? Now, to figure out the moment about a traditional x-axis formula, since my function is in terms of x, I'm rotating around the x. This is the moment form that's going to be dealing with the disk washer form. I'm trying to get you give you guys ways to actually memorize the formula. So my function is in terms of x, and the moment is that tendency to rotate, teeter-totter around the x-axis, and x to x is the disk washer formula. Disk washer, instead of pi, would be rho over 2 times integral from a to b of your top function, f of x squared of your region, minus the bottom function, g of x squared of your region, dx. This is my formula. But don't forget, to get the moment about the whole thing, we're going to use my moment about this particular region, and we're going to double it. That times 2, because I'm not working about the other side. I didn't find the equation of the other side. You could, if you want to, and find the moment of this guy, and you'll figure out it'll be the same answer again. So just double up your answer on the right side here. So now, this will end up being 2 times this rho over 2 times integral. My bounds are between 0 and 10, because this is dx, 0 to 10. My top function is this line we just created, negative 4/5 x plus 8 squared, minus, what is the bottom equation of your region? It's the x-axis. The x-axis is also known as y equals 0. And so just to follow the formula, it would be 0 squared, because the bottom is the x-axis, dx. And I put the 2 there is because I'm doubling the other side. So this would end up giving me pretty much rho times, and I'm going to stick this guy on my calculator just to save some time. I could integrate it by hand, but I would have to FOIL this little section of negative 4/5 x plus 8 squared. I have to FOIL that out. So this will be math number 9, integral from 0 to 10 of, another parentheses, negative 4x divided by 5 plus 8, close parentheses, squared. You know, who cares about the minus 0 squared, dx. And I end up getting 213.33333. 213.33333. Okay? But this is Webwork. And because Webwork, you can't type a row into your answer, you're going to have to use their constant. What was the constant for rho? What was your density? 4. So rho was actually 4. So this is 4 times that 213.33333. Pretty much times 4. And that gives me, what I'm going to type into Webwork, is 853.33333. This is my moment about the x-axis. Now, so part A was, what was my total mass? The mass was 320. To calculate the moment about the x-axis, I took half the region, found its moment about the x-axis, and then I doubled it, and that's how I end up getting that, the 2 times that rho over 2, pretty much the 2's cancel. So I get rho times my integral, and rho was 4 in this problem, so I got my moment about the x-axis. Let's talk about part C. What is the moment about the y-axis? Let's go back to the region. What is the moment about the y-axis? The moment is basically a calculation to be able to figure out which way you're going to be teeter-tottering based upon your shape. The moment about the y-axis. Look at your region. What do you notice about the y-axis? It splits it right up the middle. It's symmetric on both sides. And when your y-axis is symmetric on both sides, you know what your moment about the y-axis is going to be? 0, because it's actually the y-axis is your equilibrium. It's going to sit there and float evenly because the y-axis splits it down the middle. Think about the logic behind this, what these moments actually mean. So honestly, if you use logic, I don't actually have to calculate the moment about the y-axis, okay? But if you really wanted to, because you're just big game in the formulas, you can calculate the equation for this guy, find the moment about the y-axis of that equation, that region. And then you had to come over here and find this equation and find the moment about the y-axis on this side, but you notice it's on the left side. You'll get the exact same number, but one of them is going to be positive, the other one's going to be negative. And when you add those two numbers that are the same, that are opposite signs together, guess what you get? 0. So I'm just using logic. The answer is going to be 0. But you should have known this for an answer for part D. The answer for part D is, what's the center of mass? The formula for the center of mass is the x bar comma y bar, but remember your formulas. X bar is equal to the moment about the y divided by the mass. The moment about the y is 0. The mass was 320. 0 divided by 320 is still 0. The x coordinate is 0. If you had to figure out where, look at this region. Where is the center of mass? Since we're talking about even density throughout, where's the center of mass? Where would you put it? Well, it's triangular shaped, so it's heavier at the bottom than the top. I think it's going to be, and it's going to be right there in the middle, I think it's going to be right about there. Does that make sense? Remember, this is 8 up here, so I'm thinking it's going to be, y-coordinate's going to be slightly less than 4, just because that bottom's heavier. But if you look at that point, plot that point, what's the x-coordinate of that point? It's on the y-axis. What's x equal to? Yeah, 0. Not a big surprise there. And what about the y-coordinate? The y-coordinate is going to be the moment about the x divided by the mass. And using the symmetry and stuff, I got the moment about the x to be 853.33333 divided by the mass, which was 320. Okay, there's time for the calculator now. And so there's my 853.33333 divided by the mass of 320. And what do I get? I get 2.66667, and that's going to be your y-coordinate, 2.6667. And just based upon my very sketchy drawing up here, okay, 4 is right here in the middle, so yeah, probably a little bit less than 3 actually. 2.6667 sounds good. 0, 2.6667 is going to be my center of mass. And notice this particular problem, I didn't actually work that hard with it because I used symmetry. Does that make sense? I did have to come up with the equation of the region, expect that, but I only used the one in the positive first quadrant where the first quadrant over here where the x's are positive, y's are positive. Because of symmetry, this is going to be a very similar line, but going in the other direction, negative slope there. There'll be a positive slope as this was a negative slope. But I use symmetry on this guy and I use logic. That's always a good option when it comes to doing math. Does that make sense? Questions? So again, you got a Webwork problem just like this one. So I just wanted to kind of give you guys a big hint on this one. All right? The other problem before I go on into chapter 8 was I gave you this problem last time. Something that I just made up, and I wanted you guys to take a look at it, see if you guys can do it. I gave you guys the famous inverted pyramid that is at the top is 10 foot by 10 foot, and I told you the height was 12 foot, and I wanted you to pump all the water to a distance of 3 feet above the top of the tank. The trick to this problem is, interesting drawings, but you've got to visualize the cross-section of this guy, the side of this tank. What if you looked at this tank as this inverted pyramid just sitting out there, what would it look like to you? What is the side of this tank going to look like? It's going to be a triangle. So it's a triangle, so I'm going to draw this little triangle. Okay? It is 10 foot across. So I'm going to put my coordinate axis on there, and being a triangle, I'm going to put my coordinate axis at the bottom. It's 10 foot across. If it's 10 foot across, that makes it 5 feet on this side and negative 5 feet on this side. The height of this tank was what? 12 feet? And I want to pump all this quote, unquote, water that this thing's full of to a level of 3 feet above the top of the tank. Where would that be relative to my coordinate axis? 3 feet above 12 makes it what? 15. 15 is my target. Now, so here's my picture. And you got to remember, it is three-dimensional here, so there's my pyramid, if you will. Now, calculate work. Work is equal to the sum of the delta force times the distance that you're going to have to pump. Delta force is equal to water weight times your delta volume slice. In this problem, what is water weight and why? 62.5 pounds per foot cubed because everything was measured in feet. So this is 62.5 pounds per foot cubed. Okay, times your delta volume slice. So this will be 62.5 times your delta volume slice. I'm going to come over here somewhere on my y-axis and make a little slice. And when I make a little slice and pull it out, it's going to be a box. Not to be a big surprise by that fine fact. And the volume of a box is length times width times height. The height is always delta y. The question is, what's the length? Because it's on a slant, it is 2x. If it's 2x this direction, it's 2x this direction. So, I screwed that up, excuse me. Jumped that gun. This is x, which means the whole thing is going to be 2x. Thank you. So this is 2x, but where I was going with this is, if this is 2x and this thing is square, right, what's the width going to be? Because it changes. The last 10 problems I gave you, the width was always a constant, 30 feet, 20 feet, 40 meters, whatever it was. This one's not because it changes as you go down. The width changes, and so does the length of it change. What would that be? Because it's square, also 2x. Does that make sense? That's the key right there. This is 2x because it's a pyramid. This little thing is a square. That's what I'm going to visualize here. This thing's a square, so it's 2x on this side. You told me that. That means it's got to be 2x on this side. That means your delta volume is going to be 2x times your delta y, or better yet, 4x squared delta y. So cleaning up my delta force, 62.5 times 4 comes out to be pretty nice. That is 250 x squared delta y. Does that make sense? So now, work is going to be that sum of that delta force, which is 250 x squared delta y, times that distance I'm going to have to lift. This level that we made this cut as an arbitrary y level, we're taking this level of water and lifting it to what point? 3 feet above the top of the tank, which is 15. So what's the distance I'm going to have to lift this guy? 15 minus y. Converting this into integral calculus, work is going to be the integral of 250 x squared times 15 minus y, and the delta y turns into a dy. We put that in the back. The summation turns into x. And I got a problem. Same old problem. And that problem is big old x in the middle of my dy. So I need to come up with the equation for edge of tank. Well, this goes back to that two-dimensional figure. So you got to remember, this thing has been flattened out. So we've taken our tank and literally flattened it to the xy plane. And so this is 0, this is 12, this is 5. This makes this point, comma, 5, comma, 12. They'll put this thing at the bottom. This is 0, 0. Remember, I have flattened this thing out to come up with the equation for the edge of this tank. It's a line. So being a line, I got to find the slope, which is changing y with the change in x. That'll be 12 minus 0 over 5 minus 0. That makes it 12/5. Now my equation, I'm going to use the point 0, 0 as my point. Use the point slope formula. Y minus y1 equals m times x minus x1. That'll be y minus 0 equals 12/5 times x minus 0. That means y equals 12/5 x. That is the equation for the edge of the tank. But what I need to take this equation is to convert it in terms of x, so I can substitute it into my equation to get rid of that x and put it in terms of y. So as y equals 12/5 x, that means 5/12, x equals 5/12 y. And that's what I'm going to plug in here. So work is going to be the integral of 250 times 5/12 y. And we're squaring that x, so that'll be 5/12 y squared times 15 minus y dy. And the last thing I got to do is just put bounds on this thing. What's my bounds? 0 to 12, where the water is at the top of the tank, 0 to 12. And 250 is a constant, so I'm going to pull that out front. Math number 9, the integral from 0 to 12 of parentheses 5x divided by 12, that's being squared, times another parentheses 15 minus x, close parentheses dx. And what do I end up getting? A wonderful, nice answer of 150,000 watt. Very good, foot-pounds. Did that make sense? Now, out of my 120 some odd students I have in here, you know, only one student came by and actually did the problem and wanted to look and see if this was the right answer, and he nailed it perfectly. Absolutely superb. But one, shame on the rest of you guys. He makes an A, rest of you people fail. All right, so does that make sense though? It's not difficult, but this is the kind of a problem that I'm trying to kind of set you guys up for when they make up problems for final exam. They try to create a tank that you haven't seen before, but if you've got the knowledge of how to do these problems, it don't matter what kind of tank they give you. You can figure it out. Does that make sense? The only trick on this one was because when you make your section, a little cross section, it made a square, so that length and that width happen to be the same. Okay. Well, let's go on into chapter 8.1. 8.1 is on sequences. Now, let me give you the big deal about chapter 8. Chapter 8 is on sequences and series. Chapter 8.1 is on sequences. Chapter 8.2, 8.3, 8.4, 8.5, 8.6, and 8.7 is on series. Series is the summing of a sequence. So we're going back and looking at that Riemann sum mindset, but we're focusing literally on the summation aspect of it. But first off, you got to get a handle on a sequence. And we're going to be talking about infinite sequences and stuff. So hopefully you'll watch the awesome pre-section video that Beth made for you guys on this one. And so we kind of did these particular problems before on the class video. So please take notes on that stuff. Now, in terms of the algebra review, before we get into this, again, we're talking about sequences. The big deal is your letters are going to change. Typically, sequences are based upon, not upon X, but they're going to be based upon N. And when we talk about a sequence, we're talking about putting numbers in order. And we talk about this is your first number in order, this is the second number of the order, third number, fourth. So N typically starts with 1, and this is kind of like your domain. You plug in 1, 2, 3, 4. You don't typically do fractions with it. You plug in first term, second term, because that N is a countable discrete number here. And then your output is basically your range, what numbers that you're getting when this is the first sequence, second sequence. And the trick to this stuff is, honestly, look for patterns. But when we give you an infinite sequence, we're going to get a formula in terms of N, and then we're going to try to figure out if this sequence converges or diverges. To figure out if a sequence converges or diverges, all you do is take the limit as N approaches infinity. That's going to be the trick. So back to basically doing limits, And remember, L'Hopital's rule, 0 over 0, infinity over infinity, you take the root of the top over the root of the bottom. All that stuff from Calc 1 is going to come back and haunt you. So here's part of this algebra review and a little bit of calculus review for you guys. So remember your limit laws. If I've got two different little terms with n's in them, and I'm taking the limit as n approaches infinity, I can take the limit as n approaches infinity of the first term an plus limit as n approaches infinity of the second term bn. And that works whether you got plus or minus. So when I add or subtract sequences, I can take the limit of the first guy plus or minus the limit of the second guy. When it comes to multiplication, limits work great. You just distribute the limit here. Limit is n approaching infinity of an times limit is n approaching infinity of bn is what you get, because you can just take that limit and distribute. Over two sequences, you take the limit of the first guy, you take the limit of the second guy, whether it be multiplication or division. You just have to worry about the famous number divided by 0 aspect, because remember, you can't divide by 0, so when you got division, the bottom can't be 0. Constants. When it comes to limits, again, review, constants, hold over, and pull out front. So when I take the limit as n approaches infinity of a constant times an of a sequence there, your constant is going to come out front. Your limits go where the function is. So when I take the limit as n approaches infinity of an raised to the p power, you can take that limit as n approaches infinity of the an, figure out what that is, and then just raise it to the p power for any positive power p. Okay? And an and p actually can be pretty much any power, come think of it, but an, your base does need to be positive, whatever you're getting down here. The limit is n approaches infinity of n itself. First rule of limits is always to do what? Plug it in. You plug in n as infinity, you're going to get infinity. Here's another classic one. The limit is n approaches infinity of 1 over n. You plug in infinity, first rule of limits, but 1 over infinity, when the infinity is in the denominator, where does the fraction go to? 0. Classic rule there. And the limit is n approaches infinity of 1 over n to the c power. And again, that'll be infinity to any positive power. And it should be actually positive power. You can even have fraction on anything. Any positive power greater than 0, that is. When the infinity is in the denominator, your fractions are going to go to 0. And that c is a constant there. And the limit is n approaches infinity of a raised to the n. When you plug in infinity, a is going to be any base bigger than 1, and that's supposed to be strictly greater than 1. 1 to any power is 1, so you got to be bigger than 1. 1, anything bigger than 1, and you raise it to a power, you're going to end up getting infinity. But a little side note there, if I take the limit as n approaches infinity of a raised to the n, where 0 is less than a, which is less than 1, you have a fraction. What is a fraction raised to an infinite power? You know, what's a fraction raised to a power? For example, what's a half cubed? A half times a half times a half. What do I get? An eighth, right? And looking at your fraction, you're basically multiplying out. Your denominator is getting bigger and bigger and bigger. Your numerator kind of stayed the same there. So anytime I'm doing a fraction and raising it to a power, a fraction of a fraction of a fraction of a fraction of a fraction, if you go off to infinity on this thing, you know what you're going to get eventually? 0. So when the base a is bigger than 1, you get infinity. When the base is between 0 and 1, a fraction, you're going to get 0 when you power it up. Just little limit laws from Calculus 1. All right. So here we go. The idea behind sequences. You're supposed to give a sequence, give a formula for the following sequence. We're supposed to come up with a formula. And this is math catch a pattern. But with sequences, you always start with n equals 1. So when n equals 1, you know what term I get? I get 2. When n equals 2, I get 4. When n equals 3, I get 6. When n equals 4, I get 8. This is what I'm talking about, that countable. This is the term of the sequence. But you're supposed to catch a pattern on this thing. So what do you think the next term of the sequence is going to be? 2, 4, 6. 2, 4, 6, 8. Next one's going to be 10. What's the next one? 12, 14. You catching a pattern on this thing? So how do I go from this? This is n equals 5, n equals 6, n equals 7. So if I'm just talking about n, what are we doing to these n numbers to be able to get to the other guy? What do I got to do to a 1 to get to 2? What do I got to do to 2 to get 4? What do I got to do to 3 to get 6? And it should be the same thing for every term. What am I doing? I'm doubling it, 2 times n. So your sequence an is actually 2n. You created the formula for it. Does that make sense? You need a formula for these sequences so we can ask you whether this thing converges or diverges. Once you get the formula, then you can do your limit. Look at the next guy. N equals 1, I get 1/5. N equals 2, I get 1/25. N equals 3, I get 1 over 125. Well, if you can't catch the pattern, the trick is, hey, take whatever you got and kind of factor it, break it down, see what kind of pattern you got. Well, 1/5 is not much I can do for you there, but 1 over 25 I can. What's 25? 5 squared. And what's 1 over 125? What's 125? Catch a pattern here. It is 5 cubed. So if I continue with this pattern, I can get a formula for an, for whatever nth term in your sequence is going to be. We seem to be, we're getting 1 over 5 to the n power. Does that make sense? Or you could have written it also this way, and I'll put this in big word or there. It's the same thing as 1/5 to the n power, because 1 to any power is 1, so there you go. You accepted both ways. Look at your next one. 3, 5, 7. We only gave you 3 of them, but you're supposed to catch a pattern. 3, 5, 7. So the trick is n equals 1 is 3. N equals 2 is 5. N equals 3 is 7. But what is the pattern on 3, 5, 7? What's the next number in the sequence? 3, 5, 7, 9. Next one. 11. Next one. 13. What numbers you seem to be getting here? The odd numbers. If you look back over here, the 2, 4, 6, 8, those were even numbers. Okay? So what do I got to do to get the odd numbers? Well, the trick on getting go from even to odd is very simply. You either add or subtract 1. That'll take an even number and make them odd. Which one am I going to do here? To go from n equals 1 to get 3, your an would be equal to 2n. Get the even guys. So when I plug in 1, I get 2. But if I want 3, I need to add 1 to this guy. And then I check it. Plug in n equals 2. 2 times 2 is what? 4 plus 1 is 5. One more check. Plug it in. 2 times 3 is 6 plus 1 is 7. This becomes my formula. Again, key to math, catch a pattern. Even, odds. Now the next one tends to frustrate some students here. 1/2, 3/5, 5/8, 7/11, ... You got to come up with a formula for this thing. So first thing I write down is n equals 1, I want 1/2. N equals 2, I want 3/5. N equals 3, I want 5/8. And they gave me one more, n equals 4, I want 7/11. ... I'm going to come up with a formula for this thing based upon n. Well, first off, when I look at this thing, I notice that it's a fraction. And both my numerator and my denominator are changing. So I'm going to do a fraction. And then I'm going to focus on the numerator, and then I'm going to focus on the denominator, and hopefully when I put them together, I should get a sequence formula for the whole thing. Look at these numbers. 1, 3, 5, 7. What is the pattern for the numerators? These guys are the odd guys again, but I'm starting with n equals 1, I want 1. A formula for odd is 2n, either plus 1 or minus 1. So if I start with 2n even, when I plug in 1, I get 2, but to get back down to 1, I got to subtract 1. And I check it out. Don't worry about the denominator, just focus on the numerator. When n equals 1, 2 times 1 is 2, minus 1 is 1. N equals 2. 2 times 3 is 6. N equals 2. Let's see here. 2 minus 1. 2 times 1 is, let's see, n equals 1. 2 times 1 is 1, minus 1 is 1. Plug in 2. 2 times 2 is 4, minus 1 is 3. Plug in 3. 2 times 3 is 6, minus 1 is 5. Plug in 4. 2 times 4 is 8, minus 1 is 7. It worked. Now look at your denominator. 2, 5, 8, 11. What's the pattern? Well, first off, if you can't catch a pattern, look to see if the difference between the first term to the second term is consistent or not. If it is, that'll be the constant that you always multiply by. Have you not noticed that 2, 4, 6, 8, I'm differing by 2 each time. That's 2n. 3, 5, 7, I'm differing by 2 each time, so there's your 2n, and then I have to just do my adjusting factor to get it on the right foot. The numerator, 1, 3, 5, 7, it's differing by 2. So it's 2n, and I just have to adjust it, minus 1, plus 1, or whatever I got to do. This one's minus 1 to get my terms. But 2, 5, 8, 11. What are we differing by each time I move up? 3. So this is going to be 3n, but then I'm going to check it. When I plug in 1, I'm going to get 3 times 1, because 3 is my difference between each term, but I get 3. How do I get a 2 out of a 3? What do I got to do? Subtract 1, and then I check it. Plug in 2. 3 times 2 is 6, minus 1 is 5. It works. One more time just to make sure it's working. 3. 3 times 3 is 9, minus 1 is 8, and 3 times 4 is 12, minus 1 is 11. And then when I put the whole thing together, this is my formula for it. Now, in this concept of the new notes that we wrote up for you guys, the difference between functions and sequences are slightly different. With a function, you plug in quote-unquote all real numbers. So if I happen to have that first one, the formula was 2n. If I look at it as a function 2x, you can plug in any kind of number you want to in for x, all real numbers. When x is 0, I get 0. When x is 1, I get 2. And then I connect my dots, and then I connect all my points, because when x is a half, I'm going to get a half. When x is 2.5, I'm going to plug it in and get 4.5. You understand? I'm actually working this particular problem out of this guy. And by the way, if I plug in 2.5, I actually get 5. Thank you. So when I plug in the numbers on this thing, it doesn't matter what numbers I plug in. Sequences are slightly different. You catch the same pattern, but you're only allowed with a sequence to plug in 1, 2, 3, 4, because it's discrete, because you're counting these guys. So when equals 1, I get 2. When equals 2, I get 4. When equals 3, I get 6. When equals 5, I get 10. It's off the page there. But you get the idea. When equals 4, I get 8. This is what a sequence looks like. It's nothing but a bunch of dots, because you can't connect the dots, because you can't plug in the fractions and stuff. You only plug in 1, 2, 3. Does that make sense? And so you talk about your domain is the natural numbers, and the natural numbers, 1, 2, 3, has that double back in look, versus all real numbers, which is that double backed R look. Does that make sense? So the difference between the two. Now, the difference between these sequences and the idea of converging versus diverging. All you do is take a limit as n approaches infinity. If you get a number, then you say the sequence converges to that number. If you get an infinity or minus infinity or two different numbers, plus or minus 12, that's positive 12 and negative 12. You can only converge to a single number. Anything else, infinity, negative infinity, or plus or minus 12, is called divergent. To converge, you've got to go to a single number. So we want to figure out if something is going to converge or diverge. You basically are going to sit there and take the limit as n approaches infinity. All right, so that first problem we came up with, the formula was 2n. To figure out if it converges or diverges, you take your limit as n approaches infinity. First rule of limits is, plug it in. What's 2 times infinity? What's 2 times infinity? Infinity. And when you get an infinity answer, what do we say? The sequence an, which equals 2n, is divergent. The answer is divergent. Look at the next one. The limit as n approaches infinity of 1 over 5 to the n. First rule of limits is plug it in. This will be 1 over 5 to the infinity. What is 5 to the infinity? What's 5 times 5 times 5 times 5 times 5 times 5, an infinite number of times? Infinity, but it's 1 over infinity. And when the infinity is in the denominator, what is it? What do you get? 0. So we would say the sequence an, which equals 1 over 5 to the n, is convergent. And when you say it's convergent, you have to tell me what it converges to. Convergent to 0. Does that make sense? convergent to 0. Divergent, you typically just put divergent on the thing. Now try this one. Take the limit as n approaches infinity of that sequence 2n minus 1 over 3n minus 1. You notice it was the answer to the problem we did before. Figure out, and the question is going to be, does the sequence converge or diverge? And if it converges, find what it converges to. So I'm going to take my limit as n approaches infinity of the 2n minus 1 over 3n minus 1 and plug it in. That'll be 2 times infinity minus 1 over 3 times infinity minus 1. 2 times infinity is infinity, minus 1 is infinity, over 3 times infinity is infinity, minus 1 is infinity. It's infinity over infinity. And anybody who's passed Calculus 1, which means all of you people, that's a kind of requirement to be in this class. So what are you going to do when you have infinity over infinity? Something in the back of your neck should rise the hairs on the back of your neck going, what's going on here? You got it, L'Hopital's rule. And my code for L'Hopital's rule is the famous L''H, and I'm going to take the limit as n approaches infinity, but the variable with these sequences is n, not x typically. It can be x sometimes, but typically it's going to be n. So you just take derivative of the top over derivative of the bottom of L'Hopital's rule and then redo the limit. Derivative of 2n minus 1 is 2. Derivative of 3n minus 1 is 3. And then you plug in your infinity. But you notice all your variables went away, so there's nothing to plug in. And what do I get? 2/3. Therefore, the sequence an, which is equal to 2n minus 1 over 3n minus 1, converges to 2/3. Does that make sense? So how nasty can we make it? Well, when they get nasty, we don't make you to come up with the formula. We'll give you the formula. So here's the one. Give the limit for each of the following sequences. Here's one. an is equal to 3 divided by the square root of n minus 4n squared plus 1 over 7 minus 8n squared. And all we're asking you is, does this sequence converge or diverge? What am I going to do? I'm going to take my limit as n approaches infinity of 3 over the square root of n minus 4n squared plus 1 over 7 minus 8n squared. I've got a sequence pretty much minus a sequence if you look at what we've got here. And when you have a sequence minus a sequence, the limit law says you can take that limit and put it in front of each part of your functions here, part of your sequences. So this would be equal to the limit as n approaches infinity of 3 over the square root of n minus the limit as n approaches infinity of 4n squared plus 1 over 7 minus 8n squared. And you just turned your problem into two different problems. Let's look at the first one. What's the limit as n approaches infinity of 3 divided by the square root of n? First rule of limits, what you going to do? Plug it in. This would give you 3 over the square root of n. And when you plug in for n infinity, it's 3 divided by the square root of infinity. What is the square root of infinity? Infinity. And 3 divided by infinity, when the infinity is in the denominator, gives you what? 0. So this first sequence term goes to 0. Now it's going to be minus. Take the limit as n approaches infinity on this one. You're going to get 4 times infinity squared plus 1, which will be infinity, divided by 7 minus 8 times infinity squared. Infinity squared is infinity, times 8 is infinity. 7 minus infinity is actually negative infinity. But luckily, L'Hopital rule doesn't care whether it's plus or minus infinity. If you got an infinity, plus or minus, over infinity, plus or minus, what are you going to do? L'Hopital it. So this is showing my work. So L'Hopital rule this guy. This will be the limit as n approaches infinity of the derivative of 4n squared plus 1 is 8n. Derivative of 7 minus 8n squared is negative 16n. And remember L'Hopital's rule. After you take derivative of the numerator over derivative of the denominator, before you plug in your infinity, clean it up. What happened to my n's? They cancel. So really this turns into the limit as n approaches infinity of negative 8 over 16. And there's nothing to plug in, and 8 over 16 is actually negative 1/2. So this gives you minus, careful, negative 1/2. Watch your signs. What's 0 minus negative 1/2? Positive 1/2. So we would say this thing is convergent to positive 1/2 is the answer. But you had to do, you see what I'm doing here? You got to do a bunch of limit laws, limit properties of this stuff. Okay? So with doing these guys, we're going to be doing a lot of limit properties and stuff. So, and just to give you guys a clue, when you got multiplication, you take the limit after each part. And we're going to be looking at some of the properties of these guys. And we're going to be looking at monotonically increasing and decreasing. We'll do these next time, but the big deal about this particular stuff is chapter 8.2. And just to show you where we're going, if you look at your notes of 8.2, which I will get to on Friday's class, we're going to start summing up the sequences. That's what you're going to be focusing on. Once you get the pattern of the sequences, then we're going to talk about how to add these guys up and be able to see if we can get a number or not. That's big time stuff. We'll see that next time. So study hard, and we'll finish up our sequence section next time and start 8.2 next time as well. So see you guys then.